Yes. Hello everybody, and welcome to my talk, Pragmatic Dependency Injections for Effects, which is admittedly kind of a dry title, but I view it as I am under-promising, but hopefully I can over-deliver and give you an interesting talk. So this will be about a library that I have developed to solve some issues we have felt working in F#. And this talk is about that library and also sort of the whys of the library, sort of which problems we intended to solve with it and how we ended up where we are. That's why it's called that. So to start with, the sort of original issue we are intending to solve is, as often the case, a case of code organization. Where do you put code? Where should code belong? Which code belongs together? Which code belongs at different parts of the application? And how does that affect the quality of the code? And code quality is, of course, a very vague concept. But you want code that is legible. You want to be able to understand what the code does. You want to be able to change the code to suit new requirements or new needs. And you want the code to be reliable in the sense that it does what you believe it does, and it does so reliably in the face of changing requirement and a changing reality. So even though you might need to interface with a dangerous outside world, you can still sort of rely on your code to do what you want, or at least if it's not able to do what you want, at least tell you why it was unable to do what you wanted it to do. So those are some qualities we want from our code. And one very, I believe at least, popular way of organizing your code is through this imperative shell functional core, or functional core imperative shell, this approach. And I believe this is a very valid approach. One issue you might have with it is that it is kind of high level. It is sort of prescriptive. It tells you how you should organize your code, but it doesn't give you that much help or guidance in how to actually achieve that. And since the original presentation, I believe, was in Ruby, you might have to translate the idea across different programming languages, of course. And as an aside, I believe the name is not bad, but it's a bit unfortunate in the sense that, to me, imperative is actually not in opposition to functional code. To me, the opposite of imperative is declarative. And functional code can be both imperative and declarative. The imperativeness or declarativeness only deals with how you state the solution to your problem, while if the code is functional or not, that depends on whether or not it is free from side effects, really. And imperative code can absolutely be free of side effects, and certainly free of observable side effects. So in that sense, the naming is a bit unfortunate. But in my view, I interpret it as we want a functional core that is free of side effects, and then the shell, that's where we place all kind of code that have side effects. So code that affect the outside world or depend on the state of the outside world, or depend on state at all, really. But that brings up the question, how do you connect the shell and the core? Do we have some kind of layer in between, and what does that look like? And yeah, As an aside, in the object-oriented world, the way they solve that problem, the connecting problem, is through dependency injection. And my experience with dependency injection is that in the functional world, it is a bit of a weird fit. But in the object-oriented world, there really isn't a better solution that I have seen. I have never found a better solution. So if I was working in an object-oriented language, I would probably use dependency injection. But it has certain issues. Some things get kind of gnarly in this. Not so much that you can't really wire things up and have it work, because you can probably write tests to get a decent amount of confidence that your wiring up of dependencies will work. But rather, how do you organize your dependencies? Fine, you have an interface for them, sure. But in order to call them, you probably do something like constructor injection. But then, how many constructor arguments do you accept before you say this is too much? Is the limit at like 5? Is it 10? At previous workplaces, I have seen like a limit at 20 constructor arguments before people felt that it was too unwieldy. And again, also, how many methods should your side-effecting interfaces have? Some guidance say that you should have as few as possible in order to be able to reason about who uses what, who depends on what. But it seems to be this conflict. Either you have a lot of interfaces with a single method, and then you get these constructors with 20 arguments, or you have a few couple of interfaces that you depend on, but then they will be kind of fat interfaces with a lot of methods, and they are injected everywhere, and not all injection spots will depend on all methods. And it will be a bit of a mess. And also, to glue them all together, you, at least in my experience, you tend to create this service that only exists in order to take a lot of things through its constructor and then glue it together in some hopefully reasonably named method that you can understand. And it's kind of hard to reuse those methods, really. Sure, you can inject that service itself, but then you sort of just push the problem in front of you. So I still believe this is the best approach for an object-oriented language, but I believe also that it has a lot of drawbacks, and I believe we can do better. But in the functional world then, how would we solve this organizational problem if we do not use dependency injection? Maybe you have seen this before. My view of free monads is maybe not the most positive, admittedly. Monads are fine, I guess, but if you add a lot of bespoke monads to solve your different flows, such as using free or any kind of interpreter-like patterns based on monads, really, in my experience, having worked in some code bases that did something like this, is that you end up with a lot of stacked monadic effects on top of each other, and it gets kind of hairy to resolve it. And if you try to do like the free interpreter-based approach, my experience is that it can get really gnarly to reason about how they will resolve. I mean, at the end, if you're using free, what you're basically doing is that you are declaring some kind of abstract syntax tree and returning it. And you are expected to have an interpreter for that. And to me, the point of functional programming, as in side effect-free programming, is that it aids understanding of the code. You can have local reasoning about the code. Say, okay, this piece of code only depends on what it gets passed in, and it will always return the same thing for the same arguments. So it's the understanding part that's really important here. And sure, pure functional programming aids with that understanding, but reasoning about like an abstract syntax tree and the interpretation of that, it might be a more cognitive load compared to a very simple but with a side effect like normal function or method. So I am not sold on free. And don't get me started about continuation passing monads, because they are evil and should probably not be used unless you have a really good reason. So then the question is, what should we do instead? What could be a better approach if we don't want to do the monadic stuff, or at least not the free interpretive-based monadic stuff? But we still feel that the problems mentioned with the traditional object-oriented dependency injection, that's not the road we want to go down. Can there be some kind of compromise here? So a common initial way of solving the dependency injection problem is that you have some kind of God service or God object that you pass in. And it's an easy approach. It's easy to start that way. And once it explodes, it gets really hard to understand who uses who depends on what's really needed. And if you're doing some kind of testing where you would use stubs or other kinds of test doubles in order to test your things, how can you be sure that you substitute the things that you're really using if you're just passing in a single God thing? That would require a truly monstrous test double or mock or stub in order to like implement. But there is a way actually to solve this. And this is the library that I have devised for this. And at the core of it, it consists of these types of where like two of them are basically type aliases, really. So the way is that you have a partially applied function of a single argument. The single argument is your God object, so to speak. But you leave that generic. And then you can implement a monad for that, or you don't need to do that, but you can at least have a computation expression for that, so that you can write very linear-looking code. You don't need to see this injected God service at the usage sites. You just regard it as normal code. But by leaving that argument generic, by using the type inference in F#, we can actually accumulate the dependencies on this God object or God service through usage. And it will only accumulate the dependencies that actually are used. And you can see at each call site, okay, this effect will depend on these side effects if you model your side effects through interfaces. And then you can sort of reasonably deduce, okay, in order to run this effect, I would need to construct a service that looks like this. And it would only be the things that particular effect would depend on. Then, of course, at the edge of your program, where you sort of gather all the effects that is in your program, of course, at that site, you will still need to have a service that's capable of resolving all the things. But that's only at one single place. At all test sites and so on, you would only see the things that you actually depend on. And then by using a computation expression, it's actually kind of easy to also interact with some other types. As we can see by the type signature, this includes a task and it includes a result. So those are easily resolved or subsumed or bound in this effect context. So any usage of those types will easily be able to interact with an effect. You would not build a stack with those. You will only have the effect left. I said tasks, but of course, all task likes can work like that, and also async, in case you want to use async, can also be bound in the effect computation expression. So that's the basis of it. So how does that look like? What does it look like in practice? You model your effects through interfaces, and you can keep them really lean. It's indeed practical to only have a single method on your interface. That turns out in practice to be fully workable. And then for each effect, you need a bit of boilerplate. You'd need a provider interface. It could absolutely be automatically generated, so through some code generation tool, because it is entirely boilerplate. And then it's nice to have some kind of helper function that helps you to call your effect, like so. And again, it could absolutely be automatically generated through code generation or some other means. But my experience with code generation frameworks have been that the boilerplate is easier to deal with compared to the code generation frameworks. So I haven't felt that they really pull their weight in that regard for at least this feature. So this, in my opinion, makes organization fairly obvious. You model your effects through interfaces, and you have them at the sort of middle layer, and then you glue the middle layer together with effects, effect code that will call the effect functions to collect data. You send that data into your pure functions, into your functional core. You will get some result back, and you might then again send that result into the dangerous, impure outside world with the help of effects, if that is suitable for your application. So this is sort of the basis. This is the structure of your effectful code, so to speak. And here we can see how this could look in a very, very simple case. But we show some kind of the niceties that we get by using the computation expression. We are able to use statements, as we can see. We can use while and for loops if we want to. And we can use try with, we can use try finally if we want to, for sure. And the for loop supports both normal sex, so the normal synchronous collections, but it also supports async enumerables, so you can iterate over those as well in your effect if you have the need to do that. And there is in fact support in this library for asynchronous effects, and you can you can iterate over those as well in your effects. But the asynchronous effects, they are basically like effects. You can bind all effects in them, but instead of returning a single value, which normal effects do, they can yield many values, which can be useful in some cases. So this is sort of what the effect code would look like. And you just accumulate dependencies as you are calling your effects. And then at the edge of your program, you will run your effect. You would get back a result, and then you would take action depending on that result. The very obvious example would be some kind of like web service or similar, where you would have an endpoint. You would get in a request. That request would be handled by an effect. Depending on the effect, okay, you can return a 200 or 201, or you might return a 400 if the effect failed in some manner. Yeah. Yeah, and also, this is something that you can sort of add to the task computation expression if you want to. I don't believe it will be added in the F# core library, but computation expressions support this and bang for applicative, for applicatives, that is. And naturally, for effects, if they are based on some kind of asynchronous side effect, such as making an HTTP call or reading from a database or something similar, they are naturally asynchronous, and you can run them in parallel in many cases if the input of the next step do not depend on the previous step. And one easy way to make use of that is to use the applicative bind. So you would do let bang something and something. And if they are asynchronous, they will be executed and potentially run in parallel. And once both are complete, you would get the result of both. So it's a very easy way to make use of inherent asynchronicity in your code by just using this and bang. So that can be quite nice if you have a lot of independent side effect calls. Yes. And then this is sort of the basis that I have gone through, but there are ways to extend this if one is feeling adventurous. A lot of it depends on the computation expression. The computation expression is built in such a way that it can be extended fairly easily. And by extended, I mean that you can create your own effect-like code that sort of makes use of all the effect machinery that is in the library, but you can have your own custom run method for your computation expression. And in that one, you can do whatever you like, really. I believe you should be responsible, of course. But one thing you can do is that you can make use of the automatic ability to get the argument to a method as an F# expression. And you can configure that to not only give you the expression of the code, but also give you the value of the code. So if you get passed in a function, you get the function and you can call it the function. You don't need to do any expression compilation in order to call it. But you also get the expression, and you can parse the expression tree and get out whatever metadata that you are interested in. And And you can use that to build, for example, logging and tracing stuff automatically. You can also use this run override in order to create effects that have some kind of scoped dependency. So one example would be, maybe you want to track your database transactions in some way. You don't want to depend on some kind of ambient transaction context that's floating around in space. You want to know, okay, this is the transaction that will be used for this database call. Then you can tie that into the type signature of your effect. You can say, okay, now I have an effect with a transaction. All database calls used throughout this effect will then naturally enlist into that transaction. And once the effect runs to completion, it will commit that effect if the effect is successful, or if it's not successful, then the transaction will be rolled back. So you can sort of easily reason about which transaction affects which database calls, and so on. So that is sort of the advanced part of this library. But for casual usage, this is not something that you need to think about a lot. For casual usage, I would say this is sort of the bread and butter. You get really far with just this. This can simplify a lot of code from my practical experience, using this in a lot of code bases and also migrating some, I wouldn't say legacy, but maybe, let's say, beginner code bases, where people were sort of learning on the job how to do functional programming in F#, migrating those into this effect style of functional programming, and it has led to really clean code, really readable and legible code, and code that is easy to test as well without going insane about which dependencies do I have, how many overrides do I need to do in order to stub this out. Yes, that was sort of the main talk. Now I guess we have a couple of minutes open for questions, if you have any.
I have one question. So this sort of relies on F# computation expressions, because it kind of looks to me like this would create a sort of big stack of partially applied functions that are then sort of unraveled at the edge. But I assume that's not how it works.
Yeah. So the question was, does this depend on the F# computation expression? And in a sense, it does. So the computation expression for this, it's implemented using the fancy resumable code feature in F#, the same one that's used for the task computation expression. And so through compiler magic and inlining magic, a lot of the nested function calls will, in effect, be flattened out at runtime, and you will basically get a flat state machine. But that's an implementation detail. So I believe it is reasonable to think about it as just a series of nested function calls, because that's how it sort of works. If you're not using the computation expression, if you're instead using like the map or bind or whatever functions, and they do exist in the library as well, you are free to use them, then it will work like that, in that you will get a lot of nested function calls that will be resolved one after another.
Yeah, because the reason why I'm asking is sort of like, what are the performance, what's the performance of this? Because
yes.
I know other if you look at like the Haskell ecosystem, the effect-based libraries are sort of known to be quite slow.
Yeah, so I have not done super extensive performance testing, but I have done. And from what I have seen, the performance is quite nice. We have never had any issues with that. And the main issue that I have seen is that sometimes the inlining can fail if you make really big computation expressions. And then you get the warning that the compiler is unable to use specialized code for this. You can ignore that warning, and from what I have seen, it will mostly work because, again, I have tried in the library to implement the slow fallback that's available with this resumable code framework in F#. But in all the cases where I have run into this at real code bases, what I have done is basically refactored the effects, broken out stuff, and then the computation expressions have been they have been able to inline and optimize all the cases. So this should have quite reasonable performance characteristics. And as you may remember, the signature is that the effect is a function to a value task of a result. So we are trying to avoid allocations where possible, though of course in a lot of cases we will capture stuff and we will allocate. And I have not gone full like value task pool on this, but so far we haven't seen any performance issues with it at all. And relating to the computation expression stuff, I in my experience, the stack traces when we get them, which we sometimes do, have been fairly reasonable as well. You can sort of understand which code is calling what from the stack traces. It's not just a couple of run calls. Yes. Any other questions?
How similar is this to like SIO in Scala?
So
how does it compare to something like SIO?
I have looked a bit at SIO. I've not used it in any work capacity. I've not used it in anger, so to speak. But from my point of view, the biggest difference is that, at least historically, Java has not had a good story for asynchronous code. Now maybe they do with Project Loom. I have not used that in anger either, so I don't know. I am not myself that fond of the threading approach, even if the threads are yielding on block and all that kind of stuff. So initially, SIO was trying to also solve this problem. I never had any such aspirations with this library. This just relies on the asynchronous machinery that already exists in .NET and does not try to do anything beyond that. So no lightweight thread likes, no fibers, no nothing. It's just tasks likes, or value tasks, stuff like that. But for the type inference stuff, it's very similar to what SIO is doing. It's basically the same approach. So that part, at least, is quite similar. In practice, I have seen that SIO tends to use some kind of throwables as their error type for their result, and some kind of inheritance based on that. this framework does not have any opinion on what your error type should be. In practice, I have tended to use a discriminated union as an error type rather than a throwable or some kind of inheritance hierarchy. And that has worked well for me. Now, the difference, I guess, is that we don't have any types in F# that can promise that an error will never occur. We don't have any such types. So we cannot properly express an effect that will never fail the way you can do in CEO. But yeah, I have never felt a great need for that in practice, even though it's an appealing thought. I would like to have it if it could be easily expressed in F#, but I have not seen any approach that looks reasonable for that. So that, I would say, would be the main differences between this library and CEO from an implementation point of view.
When you infer like all the types, is it easy, or are you still able to like provide good diagnostics if there's a type error?
Most of the time, yes. Most of the time, you will get an error that says that some type does not implement the interface something. In most cases, there can be cases where it can't infer anything at all. And then you sort of need to know what you are looking for. But yeah, we're using this in basically let's say a web API. And when you're adding a new effect that is not supported at the sort of composition root or whatever you want to call it, we do get the error that this type does not implement this interface. And it's quite clear how you should resolve that. So that works well in my experience. And the type inference will allow you to omit basically all type declarations unless you want them. And you can be flexible. So if you want to, you can say that it is an effect, and then you can use underscore for the environment or the R parameter, and it will work. Yeah. All right. If there are no further questions, then I will thank you for your time. And you can, of course, ask me later if you think of anything.